Good morning and welcome live to Lincoln, Nebraska for the final presentation of the William McEllhiney Distinguished Lecture Series. Today we'll be broadcasting over the web. We have a toll-free number. It's 1-800-332-0265. Operators are standing by to take your calls. You will give them the password for groundwater and give your questions about this presentation. What I would ask you to do is hold your questions till the end of the presentation, because it is quite lengthy and there's a lot of detailed information in here. So with that being said, I'll give you the number one more time. It's up on our screen, 1-800-332-0265. The password is groundwater. Well, welcome to the 2011 William McEllhiney Lecture Series. Before we start, I want to tell you just a little bit about William McEllhiney. Mr. McEllhiney was one of the founding presidents of the National Groundwater Association. He was also a civil engineer and a groundwater contractor. And in 1948, Mr. McEllhiney and some of the other founders of the association, they saw a real benefit of having a national organization where you would have information that was disseminated throughout the country and people could share ideas and new developments. As of 2005, Franklin Electric has saw the value of this program, and they've picked up the cost of this. Now, since January 1st of this year, I've been in 28 different states and 3 foreign countries, and Franklin Electric has picked up the travel and reimbursed the NGWREF for all this. The way the McEllhiney Lecture Series works is annually a program where a presenter is chosen and asked to present their findings to the country. And I was really honored to be selected this year as the 11th McEllhiney Lecturer, and I've joined a distinguished group of people who are considered leaders of the industry, and I'm very honored to be included in this group. I want to tell you a little bit about myself here. My name is Tom Christopherson. I am the program manager for water well standards in the state of Nebraska, and since 1999 I've been involved with and an integral part of the Nebraska Grout Force test study. I was a water well contractor for over 20 years before I went to work for the state of Nebraska as a field superintendent and inspector, and now I'm the program manager, so I have a wealth of knowledge about how wells are constructed and how wells are regulated. Our series today is called the Nebraska Grout Task Force Research. Appropriately, it's titled Unexpected Results and New Solutions. And this lecture series is about a research project that was different than any research project you've ever known. Most research projects start off with a hypothesis, a budget, and a well-formulated idea where they want to end up. Well, this research didn't start out that way. This research was developed upon need, and need about new solutions for unexpected results. It's more of a story, so if you stay with me for the next hour and 15 minutes, I'm going to tell you a really neat story about what happened to me in my state. I'm going to visit with a little bit for our folks who are joining us over the web about Nebraska. You see where Nebraska is located, right in the heartland of the U.S. Some facts about Nebraska. Us locals pronounce it Nebraska, not Nebraska, not Nebraska, but Nebraska. It comes from an Oto Indian term meaning flat water. Our size of our country. I've been across the country and the world, so excuse me for that. The size of our state's pretty modest. We're 490 miles by 240 miles, about 200,000 square kilometers. And our highest point of elevation is about 5,400 feet above sea level. Our lowest point is 3,200 feet above sea level. So if you take that 2,000 feet of elevation, stretch it over 490 miles, you can see why the Oto Indians called it flat water. There's not much drop there. Nebraska is known as a groundwater generator. For every gallon that flows into our state, 4 leave our state. That's because we're ideally located right in the middle of what the pioneers called the Great Inland Sea. Most of our deposits are sedimentary, and that allows us to create water, to store water. We are perfectly situated between the Rocky Mountains to the west and the Gulf of Mexico to the south. When the storms come over the mountains, the cold fronts are very dry, and they clash with this warm, moist air mass from the Gulf, and we get tremendous thunderstorms in our state, blizzards in the wintertime. So we get that precipitation in big amounts. Some more facts about Nebraska. We got about 1.7 million people in our state. 1.2 million of those people rely on groundwater for their daily use. 2/3 of our population is located in the eastern portion, or the eastern quarter of Nebraska, mostly in two counties of Lancaster and Douglas County. Our economy is agriculture based. We have industry and manufacturing that supports that agriculture. We average a $3.2 billion in income in our state. 40% of that comes from the sale of cattle and calves. 31% of that comes from the growing of corn to feed those cattle and calves and producing ethanol and other corn products in our state. 14% of it comes from growing and selling of soybeans. And 4.3% comes from the sale of hogs. Our natural resources, our greatest natural resource, is our groundwater. We don't have the forests, we don't have the mountains, we don't have the beautiful sceneries that I've seen across the country and other states, but we do have more groundwater than a lot of states combined. The USGS estimates that if we could bring our groundwater to the surface, we would have a lake surface larger than Lake Superior, Lake Michigan, and Lake Huron combined. It would be the biggest lake between the Great Lakes and the Great Salt Lake. For our grains, we have 94,000 registered irrigation wells in our state. Disperse those over 93 counties, we average about 1,000 irrigation wells per county. As of 2006, 40% of our cropland was irrigated, and we have just either surpassed or matched California's leading groundwater irrigating state in the country. Livestock, we have the unique designation of having more cows in Nebraska than people. I've always said, if cows could vote, we'd only be eating chicken in Nebraska. To give you an idea about our groundwater use, you can see that 92% of our groundwater usage is for irrigation. When our center pivots are pumping, we're using about 7.5 billion gallons of water per day. That's a huge amount of water. Our domestic usage, about 5% of that total, about 400 million gallons of water for our cities and towns and private farms. Our livestock get about 110 million gallons per day, and industry gets about 11 million gallons a day. So you see we're very dependent on groundwater to support our income. Our concerns for our groundwater pollution are chemicals and other bacteria that could cause our water to be undrinkable. So let me tell you, before 1986 in this state, to drill a water well, all you needed was a driver's license and a drill rig. There was no statewide standards, there was no licensing. So our legislature decided, in order to protect this great natural resource of ours, they passed the Water Well Standards and Contractors Licensing Act. The purpose of that act was to protect the groundwater, and another purpose was to promote the efficient usage of that groundwater. In 1999, after we've had standards for almost 11 years, we determined our first grout standard were pretty inadequate. Our first grout standard was a half a pound of bentonite per gallon of water. It was not sufficient in order to protect our groundwater. So we needed to improve our grouting and improve our requirements. We looked at other states for case histories and field experience and what they did for protecting their groundwater. And what we found was, they told us, rely on this. Full-length grout provides maximum protection of the groundwater. When in doubt, just grout your hole, and all ground materials are pretty much alike. And what this did, folks, this put us in a conventional thinking mode. We kind of locked our brains in a box, and we took what other people told us for fact. We looked at the prevailing technologies for how grouts were studied prior to 1999, we found out that most of them were studied in laboratories. These were in controlled environments. There were some in situ studies that were done, but they were historically destructive, they were limited in their depth of view, and they were segmented. What they used to verify their findings in these laboratory studies, they used a technique called bond logging, and that's when they put an acoustic ping in the casing to see if there is any hollow portion behind that casing. If the grout was present, that ping would come back quickly. If the grout was absent, it took a longer time for that echo to come back. So that's how they verified their beliefs that all grout materials are alike. Full-length grout provides maximum protection of the groundwater. We were told that the two products we should look at were cement grouts and bentonite grouts. Cement grouts because they provide super structural stability to the well casing and the borehole, and bentonite grouts because they're more flexible, they're more pliable, and in the sedimentary deposits, they will rehydrate. So we looked at these. Cement grouts we found were considered a universal grout. You could use them in all kinds of applications. Water quality didn't affect them. Ground quality didn't affect them. Their drawback was they had limited cracking, but it was mostly a horizontal cracking, and it bonds to all types of materials. I mean, anybody who's poured a sidewalk or mixed concrete knows that concrete sticks to their shovels, sticks to their wheelbarrows. It's really nasty stuff. The bentonite grouts, we were told, they would also crack, but they were limited in that cracking and shrinkage. But the big drawback was you could only pump about 20-25% of active solids in a bentonite grout. But the redeeming factor was bentonites rehydrate when they get wet. That's what they do. They swell up and they'll repair themselves. So, based on this conventional thinking, the state revised the standard in 1999, and we adopted the national belief. We took as the bentonite grouts a 20% active solids bentonite. It had a permeability standard of 1 × 10⁻⁷ centimeters per second. And we felt pretty good about this. We now joined the rest of the country in providing groundwater protection. Well, shortly after that, the bentonite industries came to us and said, we've put a lot of money and a lot of research in a grout product that's less than 20% solids. It has the same characteristics as a 20% solids, has the same gel strength, has the same permeability standard, and now they can't use it in Nebraska. So, with the bentonite industry's cooperation, the state of Nebraska decided to construct the ultimate well. This was going to be the way everybody should make wells. And for the first time, we held a demonstration at the University of Nebraska. What you're seeing on the screen is the first time anywhere a water well has been filmed from the inside out during its construction. By using clear PVC casing that was normally used for food handling, processed cheese and milks and things, we took advantage of this clear PVC to see how grouts would be affected in the ground and how to properly make the perfect well. What you're seeing on the video now is the gravel pack has just been placed over the top of the screen, and we've just opened a bag of bentonite chips and poured those down the borehole. They're a free fall chip. We poured them in a real deliberate fashion, and what we really wanted to see was how these chips form a seal, because this is a product we use a lot in Nebraska and have used a lot since 1986. We wanted to see if the chips would align themselves, if they would make a good seal, if they would bridge, if they would impact the gravel pack. And as you can see, the chips kind of find their own place in the borehole. They align themselves in a real nice, orderly fashion, and they make a good, tight, homogeneous, uniform seal. We were really happy about this. This was really encouraging. So now we decided to start pumping our grout slurry. And you can see our grout slurry is coming up in a very quick manner, just like you want bentonite grouts to do. They come up the borehole in a rapid fashion. They evacuate everything out in front of them that's liquid. And you can see the grout itself has got a nice kind of a pudding consistency to the grout. It's looking really good. In fact, it came up the borehole so fast, it outpaced our camera. So once we caught up with the top of the column, we watched how the grout migrated up the borehole. When the grout would meet an obstruction, say a piece of bentonite that stuck to the side of the borehole wall, or some cuttings that didn't quite get cleaned out, the grout, instead of evacuating it, would just entomb it. It would surround it and place it and kind of make it part of the grout column. This was the ultimate well, folks. This was how we make monitoring wells in Nebraska. This is full-length grout to provide maximum protection to the groundwater. We were very excited about this. Wow, look what we did. Until we went back 14 months later to follow up on this. Most of that grout column was missing. It's gone. And this is how you get started in research. You create a demonstration illustrating this industry's best standards, their best science, with a technology that's never been used before, the clear casing. Now we can see what's happening, and we found out that grouts don't stay static. So, to verify our standards and to move forward, we started thinking about other conventional thinking and a historical perspective on this. All these statements you see on the screen were true at one time in the Earth's history. The sun revolves around the Earth. That was a tough one to get people not to believe. The world is flat, Columbus. You go over there, you're going to fall off. And if man was meant to fly, God would have given him wings. And I tell you what, if that would have not been true, I'd have had a lot of train miles and shoe leather worn out this year. Because I'm really glad folks would challenge the conventional thinking. So this is what we did in Nebraska. Our study is going to change that. Our study is going to utilize this clear casing where we can see things that's never been seen before. It's a visual component. We're going to look the full length of the borehole. We're going to take this out in the real world. We're going to do in situ testing for the first time. And nothing's going to be destroyed because all we're doing is taking pictures. We're just doing observations. We can dye test this. We thought we could keep these wells for a unlimited amount of time. And in reality, we got about 8 years. And after 8 years, the casing gets cloudy and you can't get a picture. If you can't get a picture, your visual study's over. But we can use it for all types of grout materials, and we can put it in all kinds of geologic sites, and it's effective for all kinds of grout materials. And in fact, some of the findings out of this led to new discoveries beyond this study. And we'll talk a little bit more about that later on. Early on, it was felt that our study needed a mission statement. And the mission statement to keep us focused was, we are going to look at the products used for grouting wells, not the people who make the products. We're not comparing manufacturers, we're comparing bentonites, certain grades of bentonites, certain degrees of cements, and we want to study the properties and how these react. And because of that, we got great cooperation from the industry. The bentonite industries and cement industries gave us all the information and the support we needed. One thing we learned, when we made our ultimate well at UNL, we didn't do any background testing because it wasn't research. It was a demonstration of the ultimate well. So when things went bad, we found out that we didn't do anything for testing the ground, testing the groundwater. Were there contaminants? Were there conditions that would affect grouts? We didn't know. So when we chose our study sites in our state, our university went out and they took core samples of the soils. We studied those for particle size, moisture content, for any contaminants that would degrade a grout. We also studied the water quality for those contaminants and those parameters. And then when we were done with that boring, we put a monitoring well in that site, and we would monitor the fluctuations of the static water table. What increases in water table or decreases in water table affect our grouts? This is what we're going to find out. Here's our study sites. The eastern part of Nebraska, with the yellow circle and the green triangle, is going to study grouts in the glacial deposits of Nebraska. These soils have been influenced by glacial melt, They have a lot of fat clays, a lot of tight clays. They have perched water tables. They get a lot of moisture, so they are a high moisture content area of our state. It's where most of our population is centered, so we're going to study wells in that portion of it. The Grand Island site with the red square is going to study wells in the Platte Valley alluvium, the sands and gravels of our state, where most of that irrigation water is pumped from. So we're going to see how fluctuations in that water table and those deposits are affecting grouts. And then the little blue triangle and the purple circle are going to study grouts in the Panhandle or the Ogallala formations. The soils and that part of the state gets less water than the east part. We get 8 to 12 inches of moisture on average in Scotts Bluff, compared to 38 to 40 inches in Lincoln and Omaha. So we got very diverse geology, we got diverse climates, we're ready to go. And here's our sites. The northeast site, the major characteristic of the Pilger site is that it does have perched water table potentials, and it has 3 lust deposits which are very absorbent materials in the unsaturated zone. The central study area, its major feature was high fluctuations in the groundwater table, like I talked about. When those irrigation wells are pumping 7.5 billion gallons a day, the water table drops in the summertime, anywhere from 15 to 25 feet. When those irrigation wells shut off in the fall, by the springtime, that water table comes back. So we have a very dry zone that's recovering. The southwest area, we studied because it was very parched soils. Those soils were dry, they were absorbent, they were fine-grained, and we had a very unique situation where we could have a single aquifer system that was close to the surface to study these. These wells that we studied in this part of the research were all less than 100 foot deep. They were held to that because of the cost of the casing. The casing was about $10 to $11 per foot. So we had expenses we had to stay in tact with. And then the fourth feature of the southwest area is where we got into looking at grouts for our geosystems. And this is at Lake McEllhiney, the visitor center. And this unique situation gave us a very deep water table. We had an extended vadosome, so we could see how does our grout stand up to this dry environment without much water. To give you an example, this is how monitoring wells are constructed in Nebraska. This is an illustration of exactly what you saw in our video. Our screen's covered with gravel just above the top of it. There's that bentonite chip seal we saw in the video as it dropped down on the gravel pack, and then our grout column went from there to the surface. Full-length grout providing maximum groundwater protection. One thing we learned in the university study is when we wanted to find out how badly the grout was cracked, we tried to pour dye down the hole, but the dye went everywhere. So our task force came up with a containment vessel that we designed about a 4-foot deep flush buried cover, and in the bottom of that cover we poured about a foot of gravel, and our dye tube terminated in that gravel. So when we dye tested this, the dye would load the gravel and it would put a pressure, an equalized pressure on top of the grout column, so we would get a uniform standard looking at validating our grouts. The goal of this visual study was to be very objective analysis, so we went foot by foot of the borehole. Our camera surveys were performed 24 hours after the grout was placed, so we got a new picture. We came back 30 days later, 60 days later, 90 days later, so we got a nice time-lapse photography on how all this grout ages. And in doing that, we had to come up with a numerical code to put this on a graph. So we could chart it. I want to show you what that visual assessment graph looks like. You can see on the left-hand side, if the grout is given a value of 0, that means there's no data. Either you're in the flush mount or there was no data recorded. If you have a 1, that means your grout was very good. It looked just like it was a pump the day it was made. If it was given a 2, we saw some cracks. We saw some developments happening in the grout, but we still felt pretty good about its ability to perform. If you saw a 3, that meant the grout was no longer considered a grout. It had channels, it had voids, it had detachments. So what you're seeing here on this screen over here, this is an example of our northeast site, and you can see up here we had really no data. When we got over to here, from 5 to 10 feet, our grout was already degraded. Okay, it was a bad grout until we got to a little bit of a perch table right here at 11 feet, and then right away, once we got through this confining layer right here, our grout went bad again. Until we got down to another perch table, and we saw our grout come back to a 2. Pretty acceptable. We got through this confining layer, and bang, our grout goes bad again, until we get down here to static water level. Well, what that tells us is, this is the first clue about what's happening to grouts. This is the first thing that we should have been warned of about when things go bad. To give you an example, Code 1 is a good grout. That's a 24-hour picture of a bentonite slurry. And that looks just like a downhole video camera of a PVC well. There's no wrinkles, there's no inconsistencies, there's no cracks. It's almost letter perfect. That's a 24-hour picture. Code 2 on a bentonite is about a 60-day picture where we're starting to see cracks perform, starting to see some separations, we're starting to see a little bit of division, but the cracks aren't connected. We still feel it's got a good potential for being a sealable grout. But Code 3 is a picture after 90 days. And we see huge chunks of bentonite missing. We see the cracks are connected. And we no longer feel that this would provide us any groundwater protection. We looked at bentonite chips. We had some wells that were full-length grouted with chips, just to see what that would look like. Once again, a Code 1, the bentonite chips are nice and tight. They look solid. You see the discoloration of the chips as they've melded together. 24-hour picture once again. Code 2 was a 60-day picture where you see the chips are kind of pulling apart, separating, but they're still in place. But Code 3, we're showing you a picture of a major void in a chip seal. And this is where the borehole was either we had a blockage, or we had a bridging, or we had a big void behind our grout column. And either way, it's either a product or a placement issue. This is to show you how big a void you can have in a 70% active reactive solids grout. And that was over a 90-day picture. Cements are entirely a different story. Okay? Code 1 was a 24-hour picture. It's a neat cement that's nice and tight. There's no cracks, there's no wrinkles, there's no discoloration. Code 2 is a picture less than 2 weeks old. And we're already seeing vertical cracking. Now, we were told horizontal cracking is what you can expect in cements. It's a stress crack. We weren't expecting to see vertical cracking, straight up and down. That's 2 weeks. And the Code 3 was a 30-day picture. So cement grouts get to their static condition within 30 days. Bentonites take about 90 days. Once the cement's cracked, it's cracked. We're seeing detachments where the casing is pulled away, and we're seeing big voids. And what you're seeing down in the lower right-hand corner, that's a placement problem. That's where the trimming was plugged and was reinserted, and there's a water bubble right in the middle of your grout column. Okay? So it's not only just a product we're looking at, it's placement. Now our next challenge, when we went to study the geo-exchange system for closed loops, nobody makes closed loop piping that's clear, and it's never big enough to put a camera in. So in order to study the grout, we had to insert a clear sight glass right in the middle of our loops. And this did two things. This allowed us to look at the grout full length, but it also allowed us to look at a grout in a larger than normal situation of a borehole. We had to drill almost a 10.5-inch borehole for 2 3/4-inch loops, and nobody does that in the real world. So we're looking at an overgrouting situation and how that would affect our grouts. And because these loops had to be used, we had to modify our dye tank. Our dye tube actually had to go down into the borehole where our dye would be loaded right on top of the grout column. Now here's an illustration. This is out of our geo loop system in Lake McEllhiney. The picture on the left, you see the top of the grout column 103 feet below the surface. That's full-length grout, folks. That's supposed to provide maximum protection of the groundwater. This is in the site that had a very extended albedo zone. Before 1999, in Nebraska, we would gravel pack loops, and then we would top it off with 30 feet of this chip bentonite. But in order to provide maximum protection, we went to full-length grout. When we did, our contractors told us that our loops are no longer working. And it's because that grout is insulating the loops. Well, getting caught in the conventional thinking, everybody was pretty sure that's what was happening until we come up with this picture. It's not the grout that insulated the loops, it's the lack of grout that insulated the loops. These loops were hanging in dead air. And for a loop to transfer heat, it has to have contact with the ground. So when our grouts dried out and degraded, not only did it compromise the groundwater protection, it compromised the performance of our geosystems. Now, further to illustrate that, on the right-hand picture, we went another foot down the borehole and we found a family of bugs living in it. Okay? My good friend Ron Peterson from the bentonite industry looked at this and he said, this is conclusive evidence that bentonite is not harmful to wildlife. So he's trying to make a good point. He's trying to put a good spin on a bad situation, but really, if there's bugs living in your borehole 104 feet below ground, you have no chance of providing groundwater protection with that kind of grout material. So after all our studies were done, we tabulated our visual assessments, and these are the recipes that the state of Nebraska approved for grouting wells at the time. Bentonite chips looked like it did the best job. It came in just at a little over a 1. Okay, so it provided us a good representative seal. A recipe of neat cement with 6 gallons was something we had proposed in our standards, so we studied that, and it came in at about a 1.2. Cement with bentonite was a little further down the road, 1.4, and you can see this is kind of a nice 45-degree slope. But if you look at the bottom of the chart, the third one up is bentonite slurry, less than 20% solids. That's the slurry that started the whole thing. That was just as good as all the rest of them. And you can see it's averaging over a 2 to 2.2. Now there's recipes in there that are averaging over 2.6, almost a 2.8. If you're averaging over a 1-year study a 2.8 on the condition of your grout, it's no longer a grout. It's not even a good annular fill. So we are seeing some things here. We're eliminating some things. We're coming to some preliminary conclusions, but we need to validate it. Because ours is a visual study and bond logging is not going to work to validate our process, we chose the dye testing. The dye will show you where your cracks in your grout lead. We asked the state of Ohio, who's been doing dye testing for 20 years or so, what to use, and they said use a green colored dye. Green is not a natural color for groundwater. If you've got green in the groundwater, it's pretty bad. So there are other dyes that are oranges and browns and reds, and they could be confused with iron deposits. So we chose a fluorescent green dye. Our procedure was to dye test these wells for an hour or until our dye tank ran dry. We had 200 gallons of dye mixed up, whichever came first. We would meter the volume that was used and the time it took for that dye tank to run out, And what that did, it allowed us to calculate proposed maximum depth the dye could be detected. How far would it really travel in a certain period of time, and how much percentage of the grout column would be penetrated by that dye. And now you're going to see the first horror picture from the study. What you're seeing is a dye test, and that's green dye flowing right out of our dye tube. We're dye testing a bentonite slurry, and we're just coming out of the flush mount. Now this green dye is flowing about 5 to 6 gallons a minute. It's going down the borehole faster than we can show our camera. You can see the grout is cracked. It's detached. Dye is not only flowing through the grout, it's flowing between the grout and the casing. This is how we construct monitoring wells for cleaning up groundwater at the time. This was maximum grouting, providing maximum protection, full-length grout. Well, we watched this to about 9 feet, and we got pretty shocked, but now we're starting to see some ponding coming up in the borehole. And we're feeling, hey, maybe our grout column is intact at the bottom. We kept watching, but what happened was that wasn't ponding. The dye ran so fast it took the gravel out of the flush mount and took it down the borehole and bridged. That's how big the cracks were in this 20% grout. So we kept watching, hoping, and it kept looking pretty dim until we get down here pretty close to the static water table, and we do actually see ponding take effect. We do see some good news, folks. Why do I say that? Because if we don't see ponding, we know that the grout column is shot clear to the aquifer. This dye would have gone out in the aquifer. We would have never got any trace of it back. But when you see ponding taking effect, you know something's happening in the bottom that's holding that column from getting to our production zone. And if you watch the screen on the left-hand side, you'll start to see the borehole fill. So this gives us another clue. Not the entire length of the borehole is damaged. Here's another unexpected result. The screen on the left is a snapshot from that video. We get to 68 feet, we see this nice illustrated crack. Boy, look at that green dye. That's pretty easy to see right there. So we took a picture. We came back a week later. There's that green dye in that crack. Came back a month later. Same green dye, same crack. We came back 3 months later. Same green dye, same crack. And this is where we learned that bentonite slurries will not rehydrate. Once they're cracked, they're cracked. They're not coming back. Now that's different than what we were told. We were told bentonites have this absorbent quality. They get wet, they want to rehydrate and reswell. It's undetermined why this happens. It may be because in order to mix a grout slurry, you have to have shearing action to drive the water into the particle. Then maybe there's retardants built into the grout that keeps it from flashing in the grouter. But for whatever reason, if a bentonite slurry cracks, it cracks and is not coming back. A new unexpected result. I wanted to show you this slide. This is more of a site comparison. If we can go over here to the screen. This is from the northeast, the central, and the southwest. And this is based on cement grouts. And you're going to see on every chart, on every average, the northeast is at the top. The dye penetrated not as far in the northeast as it did in the southwest. In every instance, the southwest, the dye went further. This is a cement bentonite recipe. This is concrete, neat cement 1, neat cement 2, and sand cement. But when we stepped back and looked at this, we noticed there's something missing here. In the central, we don't have any movement in a sand cement. This is where we discovered we matched a grout material, sand cement, with the material outside the borehole. Remember I told you the central was all sands and gravels? So these two matched, and we got a really good result on how this grout was going to progress. Kind of looks like a football play, doesn't it? X's and O's and all this stuff. Okay, now this chart, just to re-illustrate that, based on cements again, on 1 hour and 24-hour movement, I want to show you this. This bar here is how far the die moved in 1 hour. Okay? This bar here is how far it moved in 24 hours. In almost every instance, this die went a lot farther in 24 hours than it did in 1 hour. In these two, the glacial, the southwest, this die has gone behind our column. It's already dissipated out. But look at here. This is alluvial, glacial, and southwest sites. In the alluvial site, the sand cement, we had no movement in an hour, and we had no movement in 24 hours. We finally matched the grout material with the borehole material. Another unexpected result. I showed you this chart just to give you an illustration not to trust your eyes. The column on the left, the performance column, is based on the results of the die testing. The next column, the visual column, is based on what we thought we saw. And you'll see that we didn't pick a winner. Every grout we give a value to performed differently. And that's to tell you that not all cracks are connected. Not all visual things are as bad as they look. Some look better. For example, the sand cement performed a lot better than what we thought it looked like. We saw some cracks and separations when we die tested it. It did better overall than anything. And the chips, which we thought looked better than anything, did slightly worse. But if you look at the chart again, at the bottom, to the very bottom, bentonite slurry, less than 20%. Closed loop bentonite, equal to 20%. These are high water slurries. We're seeing some indications here that solids are playing a role in how grouts perform. Our third unexpected result is we found out that neat cements will blow right through a bentonite chip seal. And this is another way we make monitoring wells. If you put a chip seal down like we saw in the video, right above your gravel pack, and then your grout column is neat cement, this neat cement has enough weight and enough characteristics, it divides the bentonite chips and it gets right down into the production zone. To illustrate that, here's another video. Now in the middle of your screen, you see the white chips as they were placed. These chips were given about 45 minutes to an hour to hydrate before we put any grout column on top of them. Now 45 minutes to an hour is probably not enough time to fully hydrate a chip, but there are conditions in Nebraska where you can't leave the borehole open much longer than that or it becomes unstable.